Okay, 2 days ago we started talking about recursion. We said that a recursive program, a function, not recursive program, but a function, is a function that calls itself. This is called simply recursion. And I showed you how a recursive function works. In fact, I showed you only how a function works really. I mean, recursion is no different than a function calling another function. What did we say? We said that when you call a function such as this one, from main, I am calling this function f, okay? I am calling this function f. All I am saying is that I am going to jump to address number 1 now, okay? But since I am going to come back, I will be back, I need to save where I am going to come back. So address number 10 will be saved on the stack. And then I need to allocate some space for returned value. What am I going to return? Okay. Also, when I start running this function, I need some space for my parameter because call by value, right? I am going to copy it there, and my local variables if there are any. So since I am using the stack, okay, first in last out structure, data structure, it works very well. Okay, doesn't matter how many times the function calls itself, it always puts the new data on top of the old one. So your stack grows and grows and grows until you hit the base case, right? Until you hit the base case, or until you are out of the stack space, in which case we call it stack overflow, and your program will be terminated. Stack overflow is not a nice thing, it's a bad thing, right? It shouldn't happen at all, and it's a stack overflow errors are the sources of security issues. Many security issues are taking advantage of stack overflow errors in systems. Okay, so we don't like stack overflow, so we try to be very careful about recursive functions. That's why they say that if you're writing security critical code, don't write anything recursive, or just make sure that it's going to end in a few recursive calls. It shouldn't be like infinitely. I mean, there shouldn't be any ways of infinitely calling a function itself. Okay, a function calling itself infinitely many times. That was we said then. Okay, so are there any questions about this piece of code and what's happening with the stack? Remember our program structure. We talked about it all the time. We said that this is our process. In this case, I put my program at the top, stack is at the bottom. I have my heap at this position, and stack grows upwards. Okay, I used to show it just the opposite, just the upside down version of this, but this is what happens. So stack tries to fill up this empty space. Our globals and the heap, it tries to fill up the empty space starting from the top, and when you are out of memory, then you are done. Okay, our operating systems, our current hardware, they are very sophisticated. Actually, everything about memory is virtual. What is virtual? I mean, a process thinks that it has 16 gigabytes of memory. But on this machine, I don't have 16 gigabytes of memory. But each process can think like that. So it is the task of the operating system with the help from the hardware to show the world like this to the programs, our running programs. So our running program doesn't care about what kind of physical memory I have, what kind of space I have. All they think that they have 16 gigabytes of memory. Of course, after a while, after I started using 4 gigabytes of memory, remember what happened to my computer? It got very, very slow because it is not easy to move pages around between my memory and the system disk SSD, right? It is not easy. It is very, very, I mean, SSD compared to our memory is maybe 1,000 times slower. So your program gets 1,000 times slower which look like it has crashed. Okay, if there are no questions, then I will move on. Don't forget about the attendance. Fill in the attendance forms. Okay, recursion is just this. Okay, divide and conquer. That's what it says. Divide and conquer. What is divide and conquer? You don't know how to solve the problem, but you know how to solve it in a very simple case. Okay, for example, the factorial. Okay, for example, in a factorial case, or adding numbers from 1 to k. Okay, you say that. Okay, this should be k. You say that if the number you give me is 0, then I know how to solve this problem. I am trying to solve this problem. I from 0 to k, add all these numbers, okay, and give the result to me. So this is my fk is this, okay. I don't know this problem. This is complicated, but I know how to solve it. If the given value is 0, I just return 0. That's it. Very easy. Okay? So that's called, what do we call this? This is called what? Base case. Okay, base case is easy to solve. And this is a very important case, because if you don't have any base cases in a recursive function, what happens? Infinite recursion. I mean, let's call it infinite recursion. There is nothing infinite about the recursion. You are going to end up using up all of your memory. So there is nothing infinite, but I mean, we call it infinite recursion. Okay. So base case, without the base case, you will definitely run into infinite recursion. So the first thing when you write a recursive function, write the base case correctly. Okay, base case is done. And then if the problem is more complicated than the base case, then what did we say? What is this problem? Divide and conquer, right? We have to divide the problem into 2 or 3 or 4 or 5 parts, okay? So I decided that I am going to divide this problem like this. Okay, for some reason I was, okay, this was k minus 1. Okay, so I'm going to divide this problem into 2. If somebody gives me the solution to this problem, fk minus 1, what does that mean? From 0 to k minus 1, add all the numbers and give it to me. And I am going to add 1 to it, and I will return it as my solution. 2 parts. The first part is this part, which I don't know the solution yet. Okay. The second part is whatever is returned, I am going to add 1 to it. So this is the easy one. If I have this one, this is the easy one. So who is going to solve this? Well, this is the exact same problem as my problem. It is exactly the same thing. Okay. It is the addition of the numbers from 1 to not k, but k minus 1. So the problem is a little bit simpler. Okay. The problem is a little bit simpler. But it is exactly the same. So I made the problem a little bit simpler. So I divided it into 2, easy part and the more difficult, but the same as my problem part. And I make this call, and it just works. That's it. That's how the recursion works, and that's how you should think about it. Never think about recursion like your stacks, your activation record. Okay. Your local variables, your return addresses. This is how it works in reality, but we like to abstract the things away, right? We don't want to think about the real mechanism itself. It's like driving a car or using this pen. When I hit this button, I know that it's going to erase whatever I am writing, right? So I don't want to think about what's happening in terms of wireless communication between this computer and that one, the driver on this operating system, and etc. It's too complicated. Recursion is complicated too. Don't think about this, okay? Only think about base case and dividing your problem into 2 or more parts, and those parts should be either very easy to solve, or they are exactly the same problem as the original problem, but only a little bit simpler. That's it. Okay. By the way, recursion is very related to induction. Remember, you're from discrete mathematics class, induction. How many induction? Induction is a way to prove theorems, right? In mathematics, induction and proof by contradiction and other type of proof mechanisms. Induction is one of them, right? They tell you that, okay, how does induction work? How does induction work? Let's say they say that, is this formula explain okay, 0 to n. Okay, is this true? Okay, so you are saying that, is this formula same as addition of all the numbers from 0 to n? Okay, how do you prove it? By induction. Okay, you tell me, how do I prove this? First, remember from your discrete class, who did you take the discrete course from? Zaferiyakis Hoca? Or you are going to take it, you are taking it this semester? Yes. Okay, you are taking it from Zaferiyakis Hoca. Okay, so he told you about the induction already. Yeah, right? Induction? Not yet? But you know it from high school or somewhere? So you said that you know induction, right? Did you say that? No, the one behind you. Who knows about induction? Okay, I'm going to teach you induction then. Induction is this. It's a proof mechanism that we use a lot in discrete mathematics or in general mathematics. If somebody gives us this, if somebody gives us such a theorem, say that prove it. Prove that this one works. You say this thing first. You say that if this is true, it should work for n is equal to 1 or 2 or 3. I can easily verify it. Okay? So for n is equal to 0 or n is equal to 1, let me see. If n is 0, okay, well, by the way, this theorem only applies for, if I do the integer division, maybe, from 1 to n, right? Not 0. Let me do this, okay? If n is 1, if n is 1, I know that from 1 to 1, it should produce me a 1, right? So I am going to put this 1 here. 1 times 2 over 2 is 1. It works. For n is 1, it works. For n is 2, I should get a 3, right, from this formula. So let's put 2 in here. 2 times 3 over 2 is going to be 3, so it works too, right? So I know that. Then I can do this many times, but I don't want to do that because I cannot do this in infinitely many times. So I'm going to assume that, let's say for n is equal to k, okay, let's assume that this holds. This is assumed. Okay. If this holds, if this is true, that, okay, from 1 to k, it is k times k plus 1 over 2 is correct. I am going to show that n is equal to k plus 1 is true. Okay, so how am I going to do that? So I know that this is true. Well, I assumed it. K plus 1 over 2. This is the addition of all the numbers from 1 to k, right? N is equal to, this is the addition of all the numbers. But I like to show, okay, k plus 1 times k plus 1 plus 1 over 2 is same as k is equal to from 1 to n, all the k's. Okay, so okay, maybe I should make this n. N is from, okay, k plus 1, and this is n. Okay, so you know the math, right? If I do this, I am going to end up with this, right? So how am I gonna do this? So I know if I do this, this is k plus 2, right? So let me do this. Let's try to prove it. Okay. So I like to see this formula. I like to see this formula somewhere here. So how am I going to do that? So let me open it up. It is k. Okay. Do you guys remember how we did that? I don't want to do the same thing. Well, I can do that. Okay. So this is k squared plus k over 2, right? And this one is k squared plus k squared plus 2k plus k plus 2 over 2, right? Is it correct? Okay. I know this part. Maybe I should just make this 2 and k here. I know this part. This part is from 1 to k, right? And the other part is going to be 2k plus 2 over 2, and 2k plus 2 over 2 is k plus 1. So what I am ending up is, I am saying that this is from 1 to k, and I am adding k plus 1 to it, so that it must be all the numbers from 1 to k plus 1. Okay? This is induction. This is induction. So these are the, whatever, if you can formalize your proof in terms of induction rules for 2 cases, for 3 cases, or even a case, you show that it works by doing that. Then assume that something works and prove that k plus 1 or k plus 2 in some cases is valid. Then that's called induction. Well, induction is a mathematical way, and if you does anybody know why this works? Why we say this is a proof?
So can I correct something here?
Yeah.
Should it be sum for the k up one and below one, and show that it is a same form as
Why?
our assumption? Because we should add them up.
I mean, you mean I can prove it in other ways?
No. In this way, we should show that some of them is the same form as our assumption in order to prove it, right? Correctly.
No, I just proved it. I assume that this part, okay, this part is valid for from 1 to k, okay, this part. I assume that, and I am adding k plus 1 to it, so it is from 1 to k plus 1. That's the proof, okay? And I am asking you, how come this is a proof? How come this is a proof? Yeah.
It's a proof because what number we assign this to k,
Yeah.
it's correct. Just not like adding some random numbers. Just some hypothetical k. It's correct for k. So any.
How do you know that it is correct for k? I mean, I assumed it, right? I assume that this is correct, but how can I make such an assumption? Yes.
If I take k equal to 2, we got a tried case, and we know it is true.
Yeah.
And we can build this one after another.
Yeah.
And we can reach the infinity.
Yes. Basically, since I showed that for n is 1 it is correct and n is 2 is correct, and I am saying that this is my assumption and I prove that this is true, right? If I can assume that for n is k it is true, then let's start from here. When n is 2, I know that it works, right? Then I can show that it is correct for n is 3. Since for n is 3 it is correct now, but I can do it for n is 4 and n is 5, and I can repeat this infinitely many times. So for any value of n, doesn't matter how large it is, this proof holds. So why suddenly I started talking about this? Because this is exactly same as recursion. In recursion, you say that my base case is that n is 1, n is 2, right? My base case says that I know the solution of this one for very simple case. Okay? For very simple case, I know the solution, it is 0. That's the base case. Then I assume that somebody gives me this solution, this is an assumption for k minus 1. All I am going to do is just add 1 to it. That's it. Just add 1 to it. That will be the case. Okay. So again, this is a mathematically proven function writing. That's why mathematics scientists, math scientists, they like recursive functions a lot, because once you write a function using recursion, this kind of method, then it is mathematically true that your function, whatever the number is, as long as enough memory, is going to work correctly mathematically. Okay, there is a part of computer science. Okay, it's a very formal way of doing things. You can prove that your functions are mathematically correct. Okay, so you don't need any testing. Remember, we test our stuff. Does it work for this input? Does it work for this input? If I click here, does it work? No, they say that let's not do it. Let's write our code in a way that it is mathematically proven that our functions are going to work all the time. Okay? It is difficult to write such code. Okay? Sometimes it is inefficient, but sometimes you have to do it. For example, for some operating systems, they did it. By the way, our beloved compiler G++, okay, GCC, it is mathematically proven that this one works. It doesn't produce wrong code. Okay? You don't need to, well, not every part of it, not every piece of it, but the core part is mathematically proven. I think it took them 10 years to prove it, okay, that GCC works. So it is much better than to write some testing code, because testing code takes maybe 6 months to write. But with the testing code, you cannot test infinitely many things. But this one is definitely true. There cannot be a bug in it, because I can prove that this function will work for any value. Why? Because for base case it works. Assume that this works, and I am going to show that this one will work too. So that's a mathematical proof for you. That's why once you write recursive function, it is mathematically sound. Yes, there was a question. Yeah.
Shouldn't the return value must be k plus f k minus 1? Is it 1 or k?
Oh yeah, that's true. Yeah, that's exactly. This one calculates. What does it do? This one doesn't calculate all the numbers from 1 to k. It just calculates the number of numbers from 1 to k, which is k. Okay, so this one calculates the numbers from 1 to k. So there are k numbers from 1 to k, right? That's exactly. So what should I write here?
K.
K or k plus 1?
K.
K, exactly, because this one. So, okay. I don't know what I was doing here, but it looks like I was testing stuff. Okay, I think I did something else. Factorial, I wrote it, I guess. Yeah, I was doing something else here, yeah. I don't remember I was doing what I was doing there. Okay, so that's recursion. That's how you write your recursive functions. So this is called divide and conquer. We talked about that. Okay, we like to use recursion on arrays a lot, because can anybody tell me why we like using recursion on arrays? For example, array search, array sort, I don't know, array merge, etc. What? So why do we like using recursion on arrays? That's the question.
We can divide the problem by pairs of
Say it louder, everybody can hear. So you can divide the problem.
by pairs of 2, and then we can build up to.
No, you are telling me how you are going to do it. I am asking you why we like to use recursion on arrays.
Easier, maybe.
Easy, yeah, easy for what?
Sorting.
I'm not talking about sorting. The question is again, why do we like recursion on arrays? Okay? We like recursion a lot on arrays. And there is a reason for it. Yes?
It is continuous.
Well, it's a sequence of numbers. I wouldn't say continuous. So, finish up your sentence.
Easy to reach one after the other.
Well, those are the features of arrays, yes. But what does this have anything to do with recursion? Well, I mean, whatever you are saying is valid for the iterative case too. I write a loop. Okay, it is continuous numbers, set of numbers, and it is easy to read one after the other. You don't have to use recursion for it.
It says elegant solution here.
What?
It says elegant solution here.
So why is it elegant? That's what I am saying. Why do we like using recursion on arrays? What is the basic thing about the recursion? It is divide and conquer. Okay? Arrays, recursion, divide and conquer. It is easy to divide an array into 2, 3, 4, 5. But I can divide the array into 2. It makes just 2 arrays, right? Or I can divide the array in just one element and the rest of the elements, right? It is easy to divide our arrays into more than one part. And if I can do that, then recursion is going to work a lot easy. For example, this one. When you calculate the string length of a string, okay, what do we do? We say that, okay, I don't know how to calculate the string length of a character string, null terminated one, but I know that it is 1 plus string length s plus 1. What is s? S is a pointer, right? S plus 1 is just the next character. So it's a recursion. It's a character of array of characters. I know the last one is the null character. So I'm going to continue calling this until hit the base case. So it is very easy to write. Why? Let's write it. Integer strlen character pointer cp. Okay, first write what? Write
Base condition.
if, tell me what is the base case.
Null character.
So what am I going to write?
CP
CP,
is equal to the reference CP is equal to null.
the reference CP is same as \0. Well, I know the solution for this one. Why? Because CP is pointing to a null character position. Then I just return what? Return 0. No characters in this string array. Okay. Otherwise, I would return 1 plus. If somebody gives me the solution for CP plus 1, right? Then I can add 1 to it, and that will be it. Okay, so that's why we like the arrays a lot with the recursion. Why? Because this is how I divided the problem into 2. This part is again difficult, but it is easier than the original one. It's exactly the same problem, but it is easier than that one. And remember the induction? Induction says that assume that, okay, somebody gives you this one, CP plus 1 is given to you, and you just add 1 to it. Okay? That's why we like to use recursion on arrays. Okay, and sorting is no different. If somebody gives you this array, 2, 5, minus 1, 7, 0, 10, 12, minus 2, 7, how am I going to divide this problem into 2? You will say that if somebody sorts this part and somebody else sorts this part, I have 2 sorted arrays. Okay, so all I'm going to do is just merge them. How do you merge 2 sorted arrays? Well, you are going to do this. Let's say if this is array number 1 and if this is array number 2 and if these are my numbers, this is minus 1, 2, 7, 5, 1, 3, 6, 10, and 11. So you would merge it very easily. You say that I am looking at this one and looking at this one. Which one is smaller? Minus 1. This is gone. Then I am looking at this one and this one. Which one is smaller? 1. It is gone. Right? So 2 and 3, it is 2. Like, you know the idea, right? 6 and 7, and all you are doing is just looking at the first elements of each array and eliminating them one by one. So you read this whole array and you read this whole array. Merging it easy. The difficult part is sorting. Okay? So for the sorting, it is exactly the same problem, but only half the size. So it's called sorting. And if you sort these 2 parts separately, using exactly the same procedure, and I would merge them, and I will end up sorting the whole array. In fact, this is theoretically, this is the fastest algorithm that you can have. And in theory says that, under some assumptions, you cannot do better than this. Okay? There is a mathematical proof that, under some assumptions, you cannot do better than merge sort. You cannot find a faster algorithm than the merge sort. Okay? It's a recursive solution. Okay? So let's write another. Well, I'm not going to write the exact code, but let's say an integer search an integer pointer array and integer k. This search function, okay, looks for this integer array. Well, maybe I shouldn't. Okay. Integer a, integer size of the array, and integer k. Okay. So this search function is going to make a search in this array, and if it returns it, okay, it will return, let's say, a Boolean true. Otherwise, it's going to return a false. Okay? So what is the base case? Tell me the base case.
If we find the wanted number, for example,
I am not the only one in this classroom. Okay, say it louder. If you want.
Okay, if we are searching for k, when we find the k on the array, we should stop. We should return.
Yeah, so tell me the base case. It looks like there is more than one base case. One is what? The simplest base case is this. I know the solution for this one. Tell him stop looking at, put that phone away. Put that phone away. Away behind your desk. Yeah. Turn it upside down, yeah. Okay, say it again.
If the reference a is equal to k, maybe return true.
Oh, yeah. You are saying that if, well, I'm not going to write the C code, okay? So the reference A is equal to K, then true, right? This is the first key.
Index argument, right?
What?
We need index argument because it's a recursion.
That's what we are saying. Like it is the reference A. So beginning of the array. At the top of the array, I have this. Okay? Maybe before this, maybe I should do this. How about if my size is 0? If size is 0, right? If size is 0, then false. So do 2 base cases, very easy base cases. If it is false, then if it is 0, then false. If it is not, if at the beginning of the array I have seen k, then true. Otherwise, I have to make a search. I have to say, otherwise, return what?
The function itself, but the increment pointer.
Search, okay, is going to be a plus 1 size and k. Is that true? Size minus 1, because my problem is a little bit smaller right now. Because if I don't do size minus 1, okay, if I don't do size, what happens?
It never stops, maybe.
Sometimes infinite recursion, not all the time. Why? Because if I see that k in my array, it's going to find it and it's going to return true. If it is not there, then since size never will be 0, I will never return a false. Okay. Well, in my memory, by coincidence, I am going to find that k, because I mean just an integer. I am going to find it, or I am going to crash. So this one might run into infinite recursion out of memory, or sometimes it crashes, and sometimes it returns the incorrect result. Okay, if I don't do size minus 1. So, I mean, first when you are writing a recursive function, first do this planning. Don't write the code. Base case, and how am I going to divide and conquer? Okay, this is our division and conquer, and it looks like I was lucky in this case. Why? Because after the search, I didn't have to do anything. Remember, previously I did what? I get the number for k minus 1. I added 1 to it, right? This one I didn't do.
Negative size also possible.
What?
Negative size argument is also possible there.
Well, yeah, maybe you are saying that size should never be less than or equal to.
Yeah.
Let's do it that way. But usually, I mean, when you send a size to a function that takes a array, usually you don't expect a negative number. If somebody sends, I'm going to send an array to you, and his size is going to be minus 10, then his problem. But yeah, it's better than safe to be better. It's better to safe than sorry. So good. Okay, so this is one good way of handling it. We could have done it the other way. Okay, we could have done just divide this problem into just in the middle. Okay, so I can say that the first part of the array search, second part of the array search, whichever returns true, I am going to return true. I can do that. Should we? I shouldn't do this, but I am going to write it that way just to show you how to write that function. So integer search or Boolean search, integer pointer IP, integer size and k. Again, if size is less than equal to 0, return false. If p is equal to k, return true. I am going to divide this problem into two just exactly. Remember, I divided it into two. In one part is I know that in the first character I couldn't find it. Okay. Now I am going to divide this problem into two by taking one character out or integer out and doing the search in the rest of it. But I am going to do this. Return search something something something, okay, or search something something something. So I am going to divide the array like this into two. This is the first part of the array, second part of the array. So how am I going to do this?
We will solve the first part first, and if it is not there, we will go to second part.
Well, I already wrote it, right?
Yeah.
So how am I going to do this? So for this one, maybe I can say IP, right? Plus 1. The first one I didn't need to look at it. K will be here again. Here is a K here too. And my size is going to be S over 2. This one is S over 2, right? How about this one? This is going to be IP plus S over 2. Okay. But I need to be careful about odd sizes and even sizes, right? If it's an odd size, tek elemanlar, çift elemanlar. So I need to make sure that there is nothing in between. It is okay to make a search on the same element. But I mean, if my original size is 7, 7 over 2 is just 3, right? And this one maybe should be plus 1. And I need to make sure that this S2 arithmetic is correct. I'm not going to talk about it for now. But I'm not saying that this is better than my previous version, but it's an implementation of recursion. Okay? So this is doing either this one or this one. Okay? Good. So there is no single way to write a recursive function. Let me give you some example. This is what does it do. Yeah, right vertical. It says that if you give me a number, what does the base case do? If the number is less than 10, I am going to write it on the screen. Okay? If it is not, I will call a function. It does whatever it does. I don't know what it does. But at the end, I am going to print the last digit of that number on my screen. Okay? So let's say my number is 9. So it is going to print just 9 on it. That's it. But if the number is, let's say, 92, it says, let's forget about this one. Okay? If the number is 92, somebody is going to put something on the screen, but at the end I am going to put 2 on my screen because n modulo 2, 92 modulo 2, 10 is 2, right? It looks like this function that we are calling is exactly the same function, only it takes the n over 2, that is, this one will take 9, okay? And it's exactly the same thing. So what I'm expecting is, okay, it will do the same thing for 9, and 9 is just 9. So whatever the number I give this to this function, as long as it is greater than 0, okay, it's going to put its digits one by one on each line separately. Okay, so if my number is 172528, it will put 172528. Okay, so how does it work? It's base case. If a single digit number, just print it. Otherwise, I am going to divide this into 2. First part and the second part. For this division, okay, it uses integer division and the modulo operators. They are very simple. In C, I have it. If I didn't have these two, my job would have been a little bit more difficult. So I am saying that I know how to print this 8 on the screen. All I am going to do is just write n modulo 10, right? But I don't know how to write this on the screen for each line separately. But I know a function that will do it. It is this function, right vertical. Okay, right vertical. And if you like to do just the opposite, if you like to do just 8, 2, 5, 2, 7, 1, all you need to do is, base case is exactly the same, right? Base case is exactly the same. And I like to put 8 first. So I would say I am going to put 8 first on my screen. Rest of them will be handled by this function, vertical n over 10, sorry. Okay? Good. So let me see if what can I show you on this chapter. Okay, recursion. Okay, this we already talked about how the recursion works. By the way, let's talk about this again. I never told you about activation records in this function analysis. I did not talk to you about stack, registers, keeping your local variables, and etc. Right? So you don't think about the complications of how the things work. It is abstraction, procedural abstraction. This one, not the object-oriented abstraction, but the functional abstraction, procedural abstraction. We don't know, okay, how the recursion mechanisms work, or we know it, but we don't care. All we care about is the rules that we have, okay? What are the rules? The rules are base case definitely there, and divide and conquer, okay? Divide the problem into more than one part, okay? And solve it using your original function. So you should divide your problem into smaller parts in a way that it is exactly the same problem as the original problem, but a little bit smaller and a little bit easier.
Please come back.
Yes.
We have two codes.
Base case and the
Shows us we saw. It shows last parameter 2 times. I think.
which one? Which one? The code that I
Az önceki kontrol.
this one?
Yes.
This one does what?
Bence son sayıyı ilk kez gösteriyor.
Does what?
I think we
It shows the last number 2 times?
yes.
No, because after this one it is else. It is not. It doesn't continue, right?
Okay.
We can, let's trace it. 1, 2, and 3, right? It is, if my number is
Code
the modified one, the one that I have modified. Okay, let's do it. If my input is 1, 2, 3, okay. So base case, no. First it's going to do this. N modulo 10 is going to print 3 on the screen, right? Then it's going to call this right vertical width n over 2, which is 1 to 12, right? So when the input is 12, it is not the base case. This one will print n modulo 10, which is 2, and it's going to call this function with just number 1, and I am going to hit the base case, right? Base case will print 1, and it will return, okay? It will return to where? Yeah, it will return and return and return. It is going to be 3, 2, 1. Why do you say that it's going to print 1?
This code.
Just type it up, okay, and see if it is there. And if it is there, just come back to me. But it shouldn't, because, as I said, this one doesn't take the number more than once. And when it reaches the base case, you are saying that it reaches the base case and it does something else? No, because I keep making it smaller and smaller all the time.
But in last step, it doesn't return anything, right? Just print.
Well, this is a void function, right? Okay, nobody returns anything. I mean, if you shouldn't do this, but if you like to think in terms of stack, at the top of the stack, when you reach it, remember how I did my recursion with the stack? It returns something, and I keep that thing in my stack. But in this case, since I am not returning anything, I am not returning a value to the caller function. It's a void one.
But it returns something empty, right?
Well, it doesn't return anything, not empty.
It doesn't say to us, but it should return to back, because it
should return, but it doesn't return anything. Returning is different than returning something. Of course it should return, otherwise there would be no recursion.
So void also returns.
Void doesn't return anything, but it returns. Of course, it should return. Okay, any questions so far? Good. If there are no questions, maybe I should take some break. Break, and after that, we will continue.
Hocam bir şey döndürmesi lazım.
Hayır ya, aynı şeyi söylüyorum. Bir şey döndürmüyor. Sıfır, hiçbir şey dönmüyor. Sadece kendisi dönüyor.
Ama mesela bunu 1-2-3'e bastırması lazım. Bunda mesela en son geri dönmesi lazım. İlk başta 3'e bastırmayacak. 2'yi bekleyecek, 2 de 1'i bekleyecek.
Hayır bak. Siyahı yukarı aldım. Arkadaş onu sormadı.
2 3 diye gidecek.
Ya bir dinlesene. Arkadaş onu sormadı. Siyahı yukarıdaydı.
Onu sormadı da ben şey diyorum. Yani bir şeyin dönmesi için bir şeyin dönmesi, yani biz görmesek de dönmesi, bir şeylerin dönmesi gerekmiyor mu?
Hayır. Hayır, bir şey return etmiyor. Kendisi dönüyor. Bir şey dönmüyor. Bunlar ekranda gördüğün şeyler. Ekranda gördüğün şey bir
En
şey.
son step'te fonksiyon bittikten sonra sonuçta geri dönüyor değil mi?
Evet.
İşte bundan bahsediyorum. Orada
Ya geri döndüğünü söylüyor bak. Geri dönüyor ama bir şey geri dönmüyor.
fonksiyon pointer'ımı bir yere dönüyor, bir şeyler olması lazım.
Tamam, öyle anlamak istiyorsan öyle anla.
Hocam bir şey sorabilir miyim?
Evet.
Şimdi burada right article dedik ya. Mesela bu fonksiyon yukarıya alsaydınız 92'yi 2 olarak alma sonuçta bu mu girerdi?
Nereye alsaydık?
Bunu 2 yukarısına alsaydık.
O zaman base case'e girmeden doğrudan çağırıyorsun. Hiç base'e girme ihtimali kalmıyor.
Ama sonsuz.
Infinite recursion orada tabii ki. Yani base case o yüzden en başta yaparız ki. Yani buraya geldik mi? Geldiysek daha devam etmiyor. Yoksa infinite recursion'a gidiyoruz. Şöyle olabilir ama. Yani şunun başına bir tane if n is greater equal to 10 deyip ona gidip base case altına yazabilirsin. Ama doğrudan right particle'da
Ben yine denedim de bana şey gibi gelmiş oldu. İşte writing içinde ondan küçükse yani son basamak 1'se geldi biri yazdı sonra çıktığında yine elde bir
çıktığında hayır şimdi bak. Eğer sen bu fonksiyonu çağırdın. 7 ile çağırdın, tamam mı? 7'yi bastı. Benim son oldu bu kadar.
oraya hiçbir sayı kanetlediği için kendine ait.
Evet. İsteği de hallettim. Ben hayır yok. Bu yabancı bir fonksiyon diye düşün. Bir gariban bir fonksiyon. Farklı bir şey bu. Bunun görevi şunu çözüm. Bunu çözersen. Tamam.
Oğlum yine tanımamışsın. Ben son bilmiyorum. Mutfakta bulacağım. Bayağı işler var. Ben gidince 6 puan. Hadi 20 puan. 15 ya da 20 gider mi? Niye? Yakında 2 puan.
Oradan benim gider. Sen error çekleri yapmışsın.
Ama 2020 model telefon. Bu arada telefonda daha pahalı internet. Faturaları 200 bin lira ödüyor.
Hayır, error çekleri yapmışsın.
Yapmaktan yeni şey var.
Okay, let's start. I'm sorry I have to leave early today. I had a meeting, I forgot to tell you. But okay, around 10 o'clock we will stop, okay? So recursion is just basically, we know how it works, but we don't like to think about it, about how it works. All we are saying is that you need a base case and you need to divide and conquer. And we are going to see a few examples of it. We looked at it, and infinite recursion, of course, we shouldn't do that. Here's an infinite recursion example. Okay, so it takes an integer, it just calls itself, and it calls itself. Question for you: does it print anything on the screen? No, right? It doesn't print anything on the screen. How about this? If I put the C out as the first line,
Only one. Or
only one.
no. Many.
So what does it do? If I like this, okay, it doesn't print anything on the screen. It keeps calling itself until the memory is out, right? But if I put C out first, would I see anything on the screen? First, it would print.
Then all zeros.
What?
Zeros.
Yeah, it will print 5 first. Are you okay? Yeah, okay. It will print 5 first, right? Then 3 if the input is 35. Then n over 10 will evaluate the 0. Then 0 over 10 is always 0. It is going to print, okay, 5, 3, 0, 0, 0, 0, 0 again. And at the end, it's going to run out of memory, and it will be infinite recursion. Okay. So we talked about the stack, and we talked about the stack overflow. And what is the alternative for recursion? It is iteration. You might say that the recursive functions are stupid. I don't want to do that. I mean, if I use a for loop or while loop, it's going to be very easy. I mean, why would I use any? Where is my coffee? I forgot. Okay. Why would I use any? Why would I use any recursion at all? Because I mean, isn't it easy to write a for loop saying that for I is 0 to or 1 to I less than n and plus I sum plus assignment I and sum is 0, right? And from 1 to n I'm adding all the numbers, okay? From 1 to n, from I am adding all the numbers, and that's it, right? So it is easy as is this. Why are we writing this in recursion? I mean, why do I need to prove this mathematically that it works and etc.? Yeah, you are saying what you are saying is correct. Yeah, most of the time we don't need to write stuff recursively, unless there are things like this. For example, let's say if you have a 3, okay, if you have a 3 like this, okay, you know what 3 is like? You wrote some 3 functions, 3 programs in your C course 101, 102, right? So what is the depth of a 3? Can you tell me the depth of this 3? Or the height of this 3? It is, I'm going to tell you, it's 1, 2, 3, 4, okay? To calculate the height of this 3, writing recursive functions is very easy. All you do is, okay, you say that I have 2 children, 1 and 2, right? I have 2 children, 1 and 2. My depth or my height of this 3 is my children's height, the maximum of them, plus 1, okay? And your children is going to do the same thing. It is very easy to write. You ask your children, what's your depth? And they will tell you, and you pick the largest one, and you add 1 to it. Just 3 lines of code. If you try to write this in iterative way, it's going to be a lot more complicated. Okay, it's going to be a lot complicated. I mean, this is very similar to string length, right? String length is 1 plus whatever the remains of it. But it is easy to write this iteratively. But if you think about more than one way of branching from the original one, like trees or graphs and that kind of stuff, it is very, very easy to write recursive functions for those kind of cases. Okay, that's why, I mean, we cannot say that don't write any recursive functions. They are difficult to think about, and you can always write a corresponding iterative function. Well, that's true. I mean, whatever you can write recursively, you can write iteratively. Whatever you write iteratively, you can write recursive, vice versa, doesn't matter. But sometimes one way is easier than the other one. Okay, and with the recursion, it is always you have this leverage of you have a formal proof that your function works. Okay, when you take this data structure course, you are going to see this over again. Okay, so we already did that, functions are returning a value and etc. We talked about this. Function power, okay, thinking recursively. Ignore details, okay? You know about them, but you ignore them. Forget how stack works. Forget the suspended computations. Yeah, it's an abstraction principle and encapsulation. You hide away the details of how recursion and stack works, okay? Don't forget about the attendance. Okay, so recursive design techniques. Okay, just 3 things. Make sure that no infinite recursion. That means that write your base case very carefully, okay, to prevent any infinite recursion. If you don't have any base case, or if your base case is not properly written, then you will have infinite recursion problems or incorrectly calculated values. I have a factorial code here. Well, it might not be a very good code, but see this one? What does it say? It says that if k is 2, just return 2, it's a factorial. If k is less than or equal to 1, just return 1. Then I am going to do this k times k minus 1 times k minus 2 times k minus 3, right? Fk minus 3. So it is not like k times fk minus 1, but I have 2 base cases. See this one? For k is equal to 2, I am handling it. For k is equal to 1, I am handling it, right? For the rest, I mean, at every iteration, I go by k minus 3. Okay? I mean, if I like to do it that way, then I can do it this way. So basically, they always say us like, what do they say? They say that n factorial is equal to n times n minus 1 factorial, right? And I am saying, well, if it is true, then this is true too. N factorial is n times n minus 1 times n minus 2 times n minus 3 factorial, right? So I am going to divide and conquer it this way. So what is the advantage of it? Maybe number of recursive calls is like a little bit smaller, like 1/3 of the recursive calls. But if you are doing such stuff, write your base case equally careful way. Okay, so write your base case, okay, and your recursive calls return the correct values and you will be fine. Okay, we talked about that, and at the end of this chapter, I have this tail recursion. Okay, well, Jakob Hoca doesn't like me talk about the tail recursion at all, but I talk about it anyway. Okay, there is a concept named tail recursion. A function, okay, is tail recursive if it has the property that no further computation occurs after the recursive call. Okay, here is one. I want to give a tail recursive example. Is our search? Yeah. Remember our search function? Where was our search function? Where did I write the search function? Do you guys remember it? Is it here? No. Yep. Okay. This is a tail recursive function. Okay. Why? Because after the recursive call, we don't do any computation. Okay? We don't do any computation. After the recursive call, whatever the search returns, I return it, right? So what does that mean in terms of stack? Think about the stack. Remember, when we return something, we put the return value to the stack, and from that stack, I take that return value, I put it in some variable, I do some calculations, and I return my things, right? But this one doesn't do that. This one just returns whatever the recursive function returns. After the return, okay, after this calling, I don't do anything. I just return it. What does that mean in terms of stack? It means that before I call this function, I can take away everything from my stack, and I can ignore my stack contents because I don't need any of my local variables anymore, right? I call this function, I send the parameters, calculated them, and whatever it returns, I'm going to return it. So before I call this function, all of my local variables are not meaningful anymore. They are all meaningless, right? I can ignore them. I can delete them. So that means what? Before I call this function search, I can deallocate my stack space. So that means I don't need any stack space for each function call. It looks like it is iterative. So this is the advantages. If you write your functions in tail recursive way, there is no out of memory error messages, there is no program crashes, because stack overflow will never happen because if the compiler optimizes it. Okay, stack overflow will never happen. So if you do it, okay, if you can do it, write your functions, recursive functions, in tail recursive way, and then the advantage is going to be you will never run out of your stack if the compiler knows what you are doing tail recursive way. Okay, so it's going to be maybe as efficient as writing it in an iterative way, and it will never run out of the stack. It will never run out of the stack. But you need to be careful. For example, this is a tail recursive case. How about this one? Is this one a tail recursive? Because the last thing that you are calling is that you are doing is a function call. No, it is not the last thing, because you are calling this function, you are getting the value back, and you are adding 1 to it. So after the function comes back, you need the stack contents, right? Because you need to continue. This is not tail recursive.
Can we convert to tail recursive? Can
we convert to a tail recursive function? Well, if you write a helper function, yes, you can. I think there was an example. I think I wrote it. Yeah. For that one, usually you need a helper function. Where is my helper function for the tail recursive case? Yep. So string length, a character array. Okay. I call a helper function strlen2. Okay, s and 0. What does it do? Let's see. It says that if if s, the reference s is \0, if s is pointing to a null character, then I just return I. I is this one. Remember how I called that? S and 0. So at the beginning I am returning a 0. Otherwise, I call and return this one. S plus 1, I plus 1. Did you get it?
Each one drives another.
What does it do? S plus 1 is just incrementing my pointer by 1, and it increments this I plus 1. This is like a counter, right? This is like a counter. I am incrementing this counter every time I do this, right? And whenever this S plus 1 reaches backslash 0, then I will return that value I. So it looks like I am using my stack space somewhere in the stack space for this value counter, the number of characters that I have in it. So this strlen2 is a tail recursive function because after calling strlen2, I am not doing anything. I'm just returning it. Okay, so I did that. Again, this is recursive base case and recursive case. It is a little bit weird. You might say that, where is my divide and conquer? I divide the problem into this, like S plus 1 is the rest of the problem, and this one is I am going to add whatever you are going to return, but I am sending the return value to the function anyways, and this function is going to return I. Okay, so using this kind of a trick, you can write your function in a tail recursive way, and tail recursion is always, as I said, if the compiler knows what you are doing, you are going to ask your compiler to optimize your code. Okay, when the code is optimized, compiler will produce a non-stack overflow version of your function. It will be as efficient as iterative functions. We like to write recursive functions because they are elegant. They are mathematically proven that they will do whatever they are supposed to do. And by the way, reading recursive functions is easier too, because you know the structure of the recursive function, right? I mean, how do you write a regular function? I can do anything in it. There is no structure in it, right? I can do anything. But for the recursive function, you look for the base case and you look for the divide and conquer part, right? That's it. It has to be that way. And nothing else can happen, okay? This is not valid for non-recursive functions. Non-recursive functions, usually they are, I mean, if they are written badly, they are as long as 100 lines, 200 lines, etc. Recursive functions are usually very, very short, and you recognize it. It is easy to write, it is easy to see, and it is easy to prove that mathematically they work correctly. Yeah?
Can we convert all recursion functions to tail recursion form?
Well, if you are clever enough, yeah. Well, it doesn't work if you are going to branch more than once. Remember the tree case? Remember the tree? The depth of the tree? You have to calculate the left side and the right side, right? So it has to come back and you have to make this comparison. So it cannot be done that way. So for some, no, you cannot. But you can take one dimension of the recursion out, and if you are branching in two ways, two recursive calls, you can drop it to one, make it a little bit easy, but you are not going to prevent it.
Can I say something about this also?
What?
So can we say that we cannot convert tree recursion to iterative loop, right?
Well, sure. I mean, they are going to be in assembly, and in assembly, well, everything is kind of... what you do is, there is a way of converting any recursive function to non-recursive ones, but in your non-recursive one, you need to implement a stack. In tree
recursive form, can we convert it to iterative?
Yeah, but you need to implement a stack. So there is a possibility of memory overflow. Instead of compiler doing the stack for you, you have to do the stack yourself. Okay? I'm sorry, I need to stop at this point. I have a meeting. So we will continue next week.